Imagine a place on Earth so vast, so alien, that we know less about it than we do the surface of Mars. A realm of perpetual darkness, crushing pressure, and temperatures near freezing, where life defies every known conventional rule. This is the deep sea, extending below 200 meters, a frontier that remains largely unknown. What mysteries does this solitary world hold? And what does its exploration tell us about the very nature of life itself? We embark on a journey into the abyss, guided by the explorers and scientists who have dared to venture into the planet's deepest, most enigmatic domain. To understand the deep sea is to grasp its extreme conditions. Below 200 meters, sunlight begins to fade rapidly, and by 1,000 meters, it vanishes entirely, plunging the ocean into perpetual darkness. The pressure is equally formidable, increasing by 1 atmosphere for every 10 meters of depth. Consider the Mariana Trench, where at 10,000 meters, the pressure reaches an astonishing 1,000 atmospheres, or 14,500 pounds per square inch. Temperatures also plummet, often hovering near freezing, between 0 and 4 degrees Celsius. These are the fundamental challenges any life form must overcome to survive here. For centuries, the deep ocean was theorized as an azoic zone, a place utterly devoid of life. The prevailing scientific consensus suggested that without sunlight, the fundamental driver of life on Earth, nothing could possibly survive. This belief held firm until the late 19th century, when a pivotal expedition set out to challenge these long-held assumptions. The journey would not only redefine our understanding of oceanography but also unveil the very first glimpses into a hidden world, fundamentally altering our perception of where life could flourish. From 1872 to 1876, the HMS Challenger embarked on the first dedicated global deep-sea expedition. This groundbreaking voyage, spanning nearly 4 years, meticulously charted the oceans, taking soundings, collecting samples, and recording vital data from previously unexplored depths. Equipped with dredges, trawl nets, and sounding lines, the Challenger's crew pushed the boundaries of what was technologically possible at the time. Their findings would systematically dismantle the azoic zone theory, proving that life existed, even thrived, at all depths, regardless of the crushing pressures and darkness. The HMS Challenger expedition's impact was monumental. Over the course of its voyage, scientists on board collected and documented an astonishing array of marine life. They discovered more than 4,700 new species, including many that lived far below the sunlit surface. These findings, published across 50 volumes of reports, provided irrefutable evidence that complex ecosystems could exist in the deep. This expedition laid the foundational understanding for modern oceanography and marine biology, demonstrating that the deep sea was not a barren void, but a vibrant, albeit enigmatic, frontier teeming with life. Despite the Challenger's incredible achievements, early deep-sea exploration faced significant limitations. The equipment, primarily dredges and trawl nets, was rudimentary by today's standards. Recovering samples from extreme depths was a painstakingly slow and often destructive process. Furthermore, the immense pressure, lack of light, and frigid temperatures meant that direct observation of deep-sea environments was impossible. Scientists could only infer the living conditions from the organisms brought to the surface. For a century, much of the deep sea remained a dark, unreachable enigma, awaiting technological advancements. The year 1977 marked a profound turning point in deep-sea biology. While exploring the Galapagos Rift in the submersible Alvin, scientists encountered something utterly unexpected: towering chimneys spewing superheated, mineral-rich water from the seafloor. These were hydrothermal vents. What was even more astonishing was the vibrant, dense community of life thriving around these vents, in complete absence of sunlight. This discovery challenged the very foundation of biological understanding and forced a radical rethinking of how life sustains itself on Earth and potentially beyond. The ecosystems around hydrothermal vents operate on a principle fundamentally different from nearly all other life on Earth. Instead of photosynthesis, which relies on sunlight, these communities are fueled by chemosynthesis. Microbes at the base of the food web extract energy from the chemical compounds present in the vent fluids, such as hydrogen sulfide. These chemosynthetic bacteria then form the basis for an entire ecosystem, supporting an array of unique organisms that have never been seen before. This discovery expanded the definition of what constitutes a habitable environment. Among the most iconic residents of hydrothermal vents are the giant tube worms, Riftia pachyptula. These incredible creatures can grow over 2 meters long and have no mouth or digestive tract. Instead, they harbor symbiotic bacteria within their bodies that perform chemosynthesis, providing the worms with nutrients. Alongside them, communities of giant clams, mussels, and unique species of crabs form a bustling ecosystem. These organisms display extraordinary adaptations to high pressure, temperature fluctuations, and toxic chemicals, showcasing life's astonishing resilience and capacity to adapt in extreme conditions. The discovery of chemosynthesis in thriving deep-sea vent communities had profound implications far beyond oceanography. It demonstrated that life does not necessarily require direct sunlight to exist. This revelation dramatically broadened the scope of places where life might be found, not just on Earth, but throughout our solar system and beyond. Moons like Europa, Enceladus, and Titan, which are thought to harbor subsurface oceans beneath icy crusts, suddenly became prime candidates for supporting life. The deep sea, in essence, provided a real-world analog for potential extraterrestrial ecosystems, fueling the field of astrobiology. While human-occupied submersibles like Alvin were transformative, the advent of remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, revolutionized deep-sea exploration in the late 20th and early 21st centuries. These uncrewed machines can descend to extreme depths, operating for extended periods without human risk. Equipped with advanced sensors, high-definition cameras, and robotic manipulators, ROVs and AUVs can precisely sample, observe, and map the seafloor. They have become the workhorses of deep-sea research, allowing scientists to explore areas previously inaccessible and gather unprecedented amounts of data. The ultimate test for deep-sea technology and human endurance lies in the Mariana Trench, home to the Challenger Deep, the deepest known point on Earth. It reaches an astounding 10,929 meters below the surface. This extreme environment, part of what's called the hadopelagic zone, named after Hades, the Greek god of the underworld, has been visited by only a handful of individuals. Each descent is a testament to engineering prowess and human curiosity, pushing the limits of what is physically possible to explore the last true terrestrial frontier. In 2012, filmmaker and explorer James Cameron made history by completing the first solo dive to the Challenger Deep in his custom-built submersible, the Deep-Sea Challenger. Cameron spent hours at the bottom, observing and collecting samples, marking only the third time humans had ever reached this remote point. His journey highlighted the personal commitment and engineering ingenuity required to explore such depths. While his dive captured global attention, it also underscored how little of the hadopelagic zone has been directly witnessed or studied, even by the most advanced explorers. Even at the extreme limits of the hadopelagic zone, life persists. In 2018, the first observation of a particular species of snailfish, Pseudoliparus swirii, was recorded at an astounding 8,178 meters in the Mariana Trench. Pushing this boundary further, a remotely operated lander in 2023 captured footage of the world's deepest fish at 8,336 meters in the Izuogasawara Trench. This yet-to-be-identified snailfish species from the genus Pseudoliparus demonstrates the incredible physiological adaptations required to survive pressures that would crush any terrestrial creature. These discoveries continue to rewrite the limits of vertebrate life. Among the most bizarre inhabitants of the deep sea are the zombie worms, scientifically known as ostacs. These extraordinary creatures were discovered feasting on whale bones that had fallen to the seafloor. Remarkably, ostacs lack a mouth, anus, and digestive system. Instead, they absorb nutrients from the bone through root-like structures that bore into the skeleton. This highly specialized adaptation allows them to thrive on resources that would otherwise be inaccessible, playing a crucial role in recycling nutrients in the deep-sea environment. Their existence highlights the diversity of life strategies in the abyss. Another captivating resident of the deep is the Dumbo octopus, *Grimpeteuthus*, named for its prominent ear-like fins that resemble the Disney character. These charming cephalopods are found at extreme depths, with some species observed as deep as 7,000 meters. Unlike their shallow water relatives, Dumbo octopuses use their fins to propel themselves through the water, often hovering just above the seafloor. Their soft, gelatinous bodies are perfectly adapted to the immense pressures, and their unique appearance makes them one of the most recognizable and endearing creatures to emerge from the deep sea's dark realm. Despite centuries of exploration and technological advancements, the deep sea remains overwhelmingly uncharted. According to NOAA estimates, less than 5% of the global ocean has been explored. This means that 95% of Earth's largest habitat is still a mystery, harboring untold numbers of species and ecosystems awaiting discovery. Each expedition brings new organisms, new geological formations, and new insights that challenge our understanding of life and Earth's processes. The sheer scale of the unexplored deep ocean presents an enormous scientific opportunity, a true final frontier on our own planet. The deep sea holds immense potential for humanity. It may contain new medicinal compounds, offering cures for diseases, or novel biological enzymes useful in industrial processes. Insights from deep-sea extremophiles could further our understanding of life's origins and resilience, informing astrobiology. However, this fragile environment faces growing threats. Deep-sea mining for valuable minerals, plastic pollution, and the impacts of climate change, such as ocean acidification and warming, pose significant risks to these unique ecosystems before we even fully understand them. The imperative for careful, sustainable management is increasingly urgent. The deep sea stands as a powerful testament to life's adaptability and Earth's enduring mysteries. From the HMS Challenger's first daring probes to the cutting-edge robotics of today, each discovery reshapes our understanding of this planet. The vibrant chemosynthetic ecosystems, the crushing depths of the hadopelagic zone, and the bizarre creatures that call it home, all underscore a profound truth: life finds a way. As we continue to pierce the veil of the deep, the challenge lies not only in discovering what's hiding there, but also in protecting this solitary, extraordinary place for generations to come. The future of Earth's final frontier depends on it.